Hey everyone, my name is Tanaka, and I'm going to show you what I've been working on for the past academic year at the Facility for Rare Isotope Beams. For this project in the Scholars program I'm a part of, I was paired with Dr. Kei Misono.
Hey.
This project was conducted at the Beam Cooler and Laser Spectroscopy Facility, or BECLA for short, at FRIB. So, what do we do at BECLA? BECLA's main undertaking is to determine the fundamental properties of radioactive nuclei using laser spectroscopy techniques. This is essential in furthering our understanding of nuclear forces and benchmarking nuclear theories. Wait. Tanaka, what's laser spectroscopy? I'm glad you asked. Let me explain. Laser spectroscopy is a technique that enables us to uniquely identify atoms, molecules, and radioactive nuclei. Can you see radioactive nuclei? No, you can't. They're too small. But through our understanding of the interactions between these particles, we can design and build a setup that enables us to see their characteristics and properties. And what I have here is a couple of graphs so we can see exactly what we're trying to figure out. The charge radius here and the charge radius of different calcium isotopes. This is mainly what we're focused on at BECLA, determining the charge radius and the shape of the nuclei of different radioactive nuclei. So this is the setup at BECLA. It looks pretty complicated, but I'll break it down for you. Basically, what we're doing is we are firing a laser at an ion beam. The ion beam will absorb frequencies from the laser and then emit them again. And from that, we produce a laser spectrum that allows us to identify the characteristics previously mentioned of the isotope. So we have a radioactive beam that comes from another part of FRIB. We direct it along this path. Here we fire the laser along with the beam. That's why it is called a collinear setup. And here is where we have the detector that detects what frequencies have been absorbed by the ion beam. And so the way the absorption works is because we're using the laser is monochromatic. That means it has one wavelength and therefore one frequency. So we need to vary the frequency of the laser. Now it turns out it's very difficult to do this with the laser itself, so we vary the speed of the ion beam. And we can do this because of the Doppler effect. And the Doppler effect is basically, in layman's terms, like when you have an ambulance approaching you and you hear as it comes close to you, the sound it produces is of a fixed frequency, but as it approaches you, it gets higher and higher in pitch, and as it leaves you, as it drives away from you, it gets lower and lower in pitch. And the pitch also changes with the speed. So by varying the speed of the ion beam, we can change the effective frequency it perceives from the constant frequency laser beam. From there, using information from the detectors, we can produce a laser spectrum and determine what frequencies were absorbed, thereby allowing us to deduce the characteristics that we're looking for, such as the charge radius of the radioactive isotopes that we're investigating.
Okay, so what did I do? Well, I made a high voltage divider.
What exactly is a high voltage divider? This guy right here. Time for some more physics. A high voltage divider works on the principle of voltage division. Voltage division is the result of distributing the input voltage among the components of the divider. A simple example of a voltage divider, as shown on the right, is two resistors connected in series with the input voltage applied across the resistor pair and the output voltage emerging from the connection between them. And as we can see from this equation, the output voltage will be a fraction of the input voltage. A high voltage divider is this principle taken to the extreme, where we have a high voltage applied across a long series chain of resistors and a voltmeter connected to the last resistor in the series. A high voltage divider can therefore be used to scale down a very high voltage so that it can be measured by a voltmeter. This is because it is very difficult to measure a high voltage directly with accuracy. The high voltage is applied across the divider, and the divider output, which outputs a lower voltage that is within the meter's input range, is measured by the voltmeter. So how does that fit into what we do at Becla? Well, we need to know the Doppler shifted frequency very precisely, because that's what we use to determine the laser spectrum. And to know that, we need to know the beam energy very precisely. And the beam energy is determined by the high voltage power supply. Therefore, we need to know the high voltage very precisely. Because we're dealing with charged ions, when we apply a high voltage across the ion beam, that raises the ions to a higher energy state, and when they return back to the ground state, they gain kinetic energy. That's how we change the speed of the beam. What's the energy? 30 kilo electron volts from 30,000 volts. What's the precision we need? About 1 volt. We need that precision because the nuclear structure effect is very small, and that's the required precision to ensure we have an interpretable laser spectrum. Any precision worse than that, and we wouldn't be able to tell any nuclear structure information. As a consequence of all this, we need a high voltage divider to measure the high voltage very precisely. Now, we already had a high voltage divider, it just stopped working properly. This is a plot of our old voltage divider, total voltage against time. As you can see, the voltage is not constant, which means we do not have control over the voltage, therefore we do not have control over the beam energy, therefore we cannot produce an accurate laser spectrum. This is a problem. We've run a bunch of diagnostics, it's a dud, we needed a new one. I'm a mechanical engineer. I like making stuff. So this task was perfect for me. I drew up some rough sketches to make sure everything was viable. Made all the 3D CAD models. Made the draft and accompanying instructions on how to create the high voltage divider. And together with my colleagues, ordered the parts and made it. Here she is, fully constructed. Starting at the top, we have this copper ball and aluminum toroid-shaped top load, and this is to ensure an even distribution of the electric field because we're applying such a high voltage across the divider. If there were any pointed edges or sharp corners, that would have a high potential which could cause arcing and potentially damage electrical components. Looking at the body, we see the acrylic tube that protects the resistors that are aligned in a helix spiral all the way down the body and rest on the 3D printed part. Down here we have the aluminum support. This version does not have the heatsink and the fan because it was not needed for its application, but the one running at Becla has that, and we can see there's a gap between the support and the aluminum support and the 3D printed structure to allow for airflow. When the fan is here, the fan blows air up along the body of the tube, and it will come through here all over the resistors and then back down and circulate to cool the whole system. So, does it work? Yes, it works. What you're looking at here in the first graph is the divider ratio plotted against time. And what the divider ratio is when we read the voltage across that last divider in the high voltage divider, that is a fraction of the input of the total voltage applied. And what the high voltage divider ratio is a scalar factor that you multiply that value you get to get the total voltage applied across the divider. So we can see that this is pretty steady through time, which is good, which is what we want. So that's an indicator that the voltage divider is performing optimally. And we compared, now we needed something to compare it to because our old one wasn't working, our old divider, so we need something to compare the new divider against to see if it's working properly, like a divider that has already been calibrated and already functions as intended. So we ordered a high voltage divider from the Metrology Institute of the Federal Republic of Germany. That is the PTV voltage you see in the second graph. And we can see that both of the graphs are pretty much in alignment. So the high voltage divider that we built performs well and is in line with the performance of the reference divider. Therefore, it is effective for use in our experiments. And we can see the comparison here of the old divider versus the new divider. We can see our old one was scattering all over the place. Its voltage, total voltage, scattering all over the place against time. That's bad because then we can't control the beam energy effectively. And the new one is pretty much straight, and that's exactly what we want. It works perfectly. So, in conclusion, the new high voltage divider works really well, and we've built multiple versions of them for different departments within FRIB for use there.
Yeah, so that's what I've been up to at the facility for rare isotope beams. I'd like to thank Dr. K. Misono for being my mentor, my wonderful colleagues Adam, Sky, and Christian for teaching me so much and helping me whenever I got stuck and being a pleasure to be around.